Right then, so these are the questions that have come up for the data representation question. So the questions for data representation topic. So here we go. A real binary number may be represented in normalized floating point binary notation using 5 bits for the mantissa, 3 bits for the exponent, both in 2's complementary binary. Convert the following binary number to a denary number. Be sure to show your workings. Right, so if you want to have a go at that, have a go at it now. So pause the video now. Right then, so it's 5 bits for the mantissa, 3 bits for the exponent. So you need to normalize that number. So let's see what it is. The exponents is the same because it represents -4. Then the mantissa is, well, you have to move the point 4 places. So from the middle thing here, you go jump. Whereas I can actually do a pointer, can't I? It goes jump, jump, and then jump. No, wait, and one more jump I meant to say. So that's 4 jumps. So 4 places, and then it becomes the 0 point. I'm not sure what that's about. Pointer options. Wait. Yeah, not sure what that is about, but. So exponent, so that's the exponent, and then you just got to move, so you've got to normalize it, so move the point to there. So 0.1 if it is a positive number, and then 1.0 if it's a negative number. Another way you could have done it is just by representing it like that, and then do value half is multiplied. So this would be, I think it's like -1, then a half, then a quarter, then an eighth, then a 16th, then that is the -4, 2, and 1. So there's the half, you get that half which is there, and then you multiply it by 2, so I would do this method here. So you multiply it by 2 to the power of -4, which equals that number. Right, so here's some more questions for you to do. Pause the video if you want to have a go at them. I'll be doing the answers one after the other. Right then, so write the denary number plus +5 in this binary format. So as you know, it's +5. It needs to start with 0.1. So in pure binary it is 104. So it's 2. Yeah, then normalize it, we get that. So it moves 4 places as the dot, 3 places, so 1, 2, 3. So the dot is normally here, then it goes 1, 2, 3. Then it is, so the exponent then is written as 0, 1, 1 as it moves 3 places. So then give us the final. Then the final 8 bits is 0, 1, 0, 1, 0, 0, 1, 1. Well then, so write in this format the largest possible binary number that can be represented. So largest positive number, so emphasis on the positive number. Another question is that would actually come up for this would be what is significant about this number, and so there's the number. And then another question would be, what is significant about this number? And you would say it's the largest possible binary number. I think that might be a question that does pop up a bit later. Oh. Give the denary equivalent of the largest positive binary number. Is that just... There you go, then. That is 111.1 equivalent to 7.5. Yeah, so that's the largest. What? I don't get that at all. I'll do some more work on it a bit later. So let's have a look at the next questions. So pause the video now if you want to have a go at it. So a real binary number may be represented in normalized floating point binary notation. Use 5 bits for the mantissa and 3 bits for the exponent, both in 2 complementary binary. Convert the following binary number into denary. Show your working. So normalize it, then just show your working. So here we go. Exponent is 0, 1, so I'm just going to go for this one since this is the method that I'm going to be using. So there's the exponent. So exponent and then this is the mantissa. So mantissa is 0.1 since there is a, so the dot would be there as it's a break in between, so then the dot needs to be moved a couple of spaces. It needs to be moved 4 spaces. No, 2, what? I don't get what I've just done. So exponent 0.1, yeah, I get that, represents 2. Mantissa needs to be that. So the dot needs to be there. Then it's get you that thing since it's going to be -1, a half, quarter, eighth, and then 16th. And just add all those together, so 1/2, 1/4 plus 1/16, which gives you 13/16. Then multiply by 2. So this is actually already, you just got to add in the decimal point. Then so 13/16 multiplied by 2 to the power of 2, since this is -1, then well, -4 actually, isn't it? -4, then 1, and you take the middle value as that is the one with the 1, which gives you the 13/4, which it will give you that answer, which is 3.25. Right then, so let's have a look at the next question. Convert the following binary number to a denary number. Show your working, so pause the video if you want to have a go at this. Right then, so convert the following binary number to denary. So you might have to normalize this, I'm not sure. I don't think you need to normalize this as it starts as 0.1. So here we go. Exponent is 101, which represents -3 because -4, then there's a 1, 2, so -4 plus 1 is -3. The mantissa 0.1, so 0.1, so there's the -1, then half, then quarter, and so on and so forth. So you just take the half, which is 0.5. Value is half multiplied by 2 to the power of -3, which equals 1/16, which equals that number. I think it would actually be a good idea though, if as well as that the fraction, if you actually do the real value of it as well. So let's have a look at the next question. Convert this binary number to denary. Show your working once again. But this time the mantissa is 6 bits and the exponent is 2 bits. So let's have a look at the answers. So convert the following binary to denary. So you can tell me. So here we go. So 0.1 represents 1 since it goes to -2, then 1, and then this is -1, a half, 8, 4 even, then 8, then 16, then 32. I'm just using my mouse to draw this on. So here we go. So exponent is 0.1, so it represents 1. Mantissa is 0.10110, since the point is there and it starts in 0.1, so you know it is a positive number. So adding all this together, so 1/2, 1 over 8, 1 over 16, 1 over 16 gets you 11 over 16, or 0.6875. So the value 11 over 16 is multiplied by 2 to the power of 1, so the exponent, which gives you 11 over 8, or 1.375. Right, so let's have a look at the next question. I can't remember if it's actually the more working out I think it might be. Right, let's have a look at the next set of questions. So, write in binary the largest positive number that can be represented in this format, and the format is the same as previous, which was a 6 bits for the mantis set and then 2 bits for the exponent. So have a go at this and see how well you do, and now let's have a look at the answers. So mantis set is 0.11111, so loads of ones and stuff like that, so that it can be 1 plus a half, which gets you that. And then the actual exponent is 1. It's just literally 1, since it's only 2 bits. So now let's move on to the next set of questions. Oh, I've messed this up. Oh well. There we go. That's fixed. Right then, so by converting each of... So you're given P, Q, and R. And you've got to convert these binary numbers to denary, and show which represents a different value, and be sure to show your workings. So you've got to use the binary number to create it into denary. So have a go at this, see how well you do. Right, so let's have a look at the answers. So here we go. P, the mantissa is 0.010. So the where am I? So the dot needs to be put there. Then the exponent, you just leave it the same, so let's convert it as is, as the point is there, so it's 0.1. Then the exponent is just 2, because there's the -4, then there's the 2, then the 1. Well then, so here is Q. Now I've actually just blurred out just so you cannot see it at the moment. So Q is 0.001, so the decimal point goes there, and it also represents the same value. It represents the same denary value as the P. Now, then the exponent for this is just, since it's 2 and 1, so -4, then 2, then 1, so that is 3. So for R, the mantissa is 0.001, so we just got to add in the dot there. The exponent is -4 though. So the binary number, the binary value is 0.0000001, which is the denary value of 1 over 256. So you need to identify that R represents a different value, and that is dependent, no. You will get the mark if the P and Q are the same. Well, if you identify that they're the same. So let's have a look at the next set of questions. So a real binary number may be represented in floating point binary notation using 4 bits for the mantissa and 4 bits for the exponent, both induced complementary binary. The numbers are normalized, so convert 0.110010 to denary, and be sure to show your workings. Then convert 1001001 to denary. So have a go at this if you want to. Well, pause the video if you want to have a go at this. Right then, so the answer is, so convert 0.110010 to denary. So the exponent is 2 as, so for the number, so 0110, so that actually the mantissa. Then the exponent is 0010. Since this is -8, then it goes 4, then 2, then 1. Then the mantissa, am I doing, yeah, then the mantissa, yeah, the mantissa is 0.11, so you need to put the decimal point there. So the normal decimal point is normally in between the mantissa and the exponent, so you've got to move it, so 1, 2, then 3. Oh, actually, have I messing up here? No, it's actually only 2. Yeah, I did mess it up. So only 2 places to the right. To the right. Oh, so yeah. Yeah, then. So then the. So 0.11, yeah. Which is the Denry value of. Have they got this one the wrong way? Because it looks like they have. Sort of, maybe. I think that might be. Yeah, that might be the new exponent. So that equals 3. So there you go. Denry value is. No, that is. Oh. There we. That's. Right, so it goes 1, 2, yeah. Then 4, then 8. So yeah, so since the decimal point is there, then the new value is like that. So then it's 1, 2, stuff like that. So then that equals 3. I'm not really sure on that. I'll try and do over the weekend. I will just do some past papers. I'll do more of these questions as well. So now the next question, convert 10010001 to denary. So the same 4-bit, same for the 4-bit mantissa and 4-bit exponent. So exponent is 0001. So as you saw up here, it's getting the one from there. Mantissa is 1.0 as it is a. Oh, it's going to be a negative number. So what you remember is that 0.1 is a positive, then 1.0 is a negative number. So, right, so what you can remember is that, yeah, so mantissa 1.0, yeah, so you just need to put the point there, and it moves one place to the right. So one place there, so it becomes 10, so 10.01, okay. Then the denary value is -2 plus a quarter equals -13/4, or -1.75. I kind of get that. So let's have a look at the next set of questions. So more of these. So convert denary number positive 2.25 to a normalized floating point binary number where it has 5 bits for the mantissa, 3 bits exponent. Then the question below that is convert the denary number positive 3.5 to binary, but then 4 bits from the mantissa and 4 bits for exponent. Pause the video now if you want to have a go at it. So let's have a go. Let's have a look at the answers. So let's see. So 5 bits for the mantissa, 3 bits for the exponent. So I can see how this is. Oh, there we go. So I can see how this is really going to go. So it's going to be 1, 2, 4, 8, 16, 32. 1, 2, 3, 4, 5, 6. Ooh. So get rid of the 32. So then there's the -4, 2, then 1. So let's see. I'm just going to quickly do it just so you can see how I'll work it out. So 0, 0, 0, Oh wait, no, it's not like that, is it? It's the point, half, then quarter, point options, ways. Remember, it's 3 bits, so half, quarter, then eighth, I believe, yes. Then 1, 0, and 0. There you go. So that should be the correct answer. Let's see. Yeah, that's pure. Yeah, I didn't normalize it. Make sure you need to normalize the thing. So that is what it is. So that is one of the first steps. But then you've got to actually convert it to this. So I did get it roughly right, since you're only really interested in these bits here. So then your mantissa is that. Then the exponent is 0.1. So that's the -4, then 2, then the 1. Now let's have a look at positive 3.5. So I'm just going to quickly do this. Then I skip to when I do it. So right then. So those are the numbers that you're going to be important on. So that is actually a 0 there. So it's 0.1110 for just here. But then it's actually the same, isn't it? Let's see if it's right. I forgot to do exponent. So yeah, so exponent. So -8, then 4, then 2, then 1. So yeah, it moves 2 places. Yeah, so it's there. So it needs to go 1, 2. So that's 2 there. So it's times 2. Well, you don't need to actually do the times 2, do you? You just need to say the -4, well actually -8 in it, -8, then 4, then 2, then 1. So then it's 0, 0, then it moves 2 places, and there we go. Yeah, so 0, so that's the exponent, the mantissa I mean, then that is the exponent. Let's have a go at some more questions. Oh, here we go. State the format of the mantissa of a normalized floating point binary number, and then give a normalized version of the number 000100011, where 5 bits for mantissa, and then 3 bits for exponent. So have a go at this if you want. Pause it if you want to have a go at it. Now, let's have a look at the answers. So here we go. Now, this is a very good thing to know. So it would be, what did I say before? Is that 0.1 for a positive? Oh, yeah. It doesn't actually say if it should be positive or not. You just got to say the exponent is adjusted so that mantissa starts with either a 0, 1 or 1, 0. It might be good though if you do actually say 0, 1 for positive and then 1, 0 for negative. So now the normalized version of this number, where 5 bits for the mantissa and 3 bits for the exponent, is 0, 1, since the decimal point is here, so you just need to go 1, then 2, so it moves 2 places. There we go. So 1, 2, 2 places, and then it becomes 0.1000. Then you just got to do the exponent. So that's the exponent. So my exponent would be -4, then 2, then 1. And since it moved 2 places, it would just be. Oh wait, what? It moves 2. Mantissa is not. I'm not getting this at all. I need to do more practice on this. So, mantissa. No, oh wait, so that, yeah, it's just getting it straight from there. And then it got normalized. Yeah, so that is the actually. Oh, right, they're doing it in steps. So you got to identify it, then it moves places. So it's now the 0, 1, 0, 0, 0. so the decimal point is here, then the exponent, but I don't get why the exponent is 0.01. Or did it? Because it didn't move. I don't get that question. I need to do more of these. Alright, so let's have a look at the next set of questions. So floating point numbers may be represented by 4 bits for the mantissa, 4 bits for the exponent. 2 numbers have been written in binary. Only one of the numbers have been normalized. So which of these have been normalized, and give your reason for your example, for your answer. Then give 2 reasons why binary numbers should be normalized. So let's have a look at the answer. So the number that has been normalized is A, as the first 2 bits are different since it start different, and then you could, well, there's only 1 mark, so let's do A as the, since the first 2 bits start with 1, 0. Now, 2 reasons why binary numbers should be normalized is due to ensure unique representation of a number, to provide maximum precision or accuracy, multiplication is more accurate. So let's have a look at some more questions. Explain what happens when the denary number positive 5 and a quarter, so positive 5.25, is converted to a normalized floating point binary number when 4 bits are used for the mantissa and 4 bits are used for the exponent. So explain what happens. So you might want to work this out as well, so you can have a visual representation. Then in question, so have a go at these questions. See if you want to do it. So the bottom one is to say, but if instead 4 bits are for the mantissa and 4 bits for exponent. So floating point binary numbers may be represented by 5 bits for mantissa, 3 bits for exponent. If instead 4 bits are used for both the mantissa and exponent, state the effect of the range and accuracy of the number that can be represented. So pause the video now if you want to have a go at it. Right, so explain what happens when the denary number positive 5 and a quarter is converted to a normalized floating point binary number is, so positive 5 and a quarter is done, so that's the so in pure binary, so it's 101.01, and the mantissa is 010101, but since only 4 bits are allowed, the mantissa would only be 0101, so 5 is stored, but not the 5 and a quarter that it actually should represent. Then the main thing is that the the values are stored, it is inaccurate, so the precision is lost. Then the exponent is 0011, so the number would be stored as 01010110. Well, what am I doing? The number will be stored as 01010011. Now, the reason why they should be, so explain the state of the effect on the range and accuracy of the number that can be represented when the 4 bits from the mantissa and 4 bits for exponent. So the question above is actually already explaining what it causes. So let's have a look. So accuracy is decreased as fewer bits are available. The range is increased as larger magnitude exponent available. So accuracy is lost due to the decrease in size of the mantissa. Then the range is increased due to the size of the exponent. So here we go. Floating point binary numbers may be represented by 5 bits for the mantissa, 3 bits for the exponent. Then, if instead 3 bits are used for mantissa, 5 bits for exponent, state the effect of the range and accuracy. So this is a question that is pretty much from be 4, but the other way, pretty much. So let's have a look at. So you can pause the video now to have a go at these. So explain why this number is important. 0, 1, 1, 1, 1, 0, 1, 1, in which 5 bits of the mantissa, 3 bits of the exponent. Explain why that number is important. I'll give you a hint that that question did actually come up a bit earlier within this video. Right, so pause the video now if you want to have a go at these. Right, and so state the effect of the range of accuracy on the number where 3 bits for the mantissa, 5 bits for the exponent. Well, the accuracy, the range is larger, but the value stored is less accurate. Then explain why this number is important for the next question. So, maximum positive number. Be sure to say positive number, as the other value that can be stored is like a really high minus number or so. So, as mantissa and exponent each have their largest values, because the first thing on mantissa is the -1. Well, this is when you convert it back. So the first bit is a -1, and it's the first bit for the exponent is a negative number, so it's -4 in this case. Right then, so I hope this video has been helpful for you, as this is the last question. I will hopefully be able to do some more stuff on this a bit later. If you want to know more about this, be sure to check out the video from Lesson Hacker, as I will do, as this is already in the playlist. So anyway guys, thanks for watching the video.